Your credentials are listed in .gitignore. So does that mean your coding agent can't see them? No. And that gap reveals exactly why a version control file can't serve as an AI security policy. .gitignore helps manage version control exclusions. That's its job. The dangerous leap is assuming those exclusions also define an agent's context automatically. They don't represent equivalent controls, and we shouldn't treat them as if they do. A file can be absent from a commit and still be sitting in the working environment available to an AI-assisted workflow. So the practical rule is simple. Credentials and other sensitive files need to be excluded explicitly from AI context. Don't rely on an ordinary repository convention to enforce a completely separate security boundary. Now, this isn't a claim that every agent ignores .gitignore. It's a warning that developers can't safely assume a version control file determines what every agent can access. That distinction changes the question we need to ask. Instead of, is this file committed? Ask, can this information enter the agent's context? Repository files are only one possible input. Coding agents can also receive network content, along with information supplied through tools. That wider input surface matters because agents can be exposed to indirect prompt injection. Manipulative instructions embedded inside material the agent reads while it's carrying out another task, and the agent doesn't need to receive an obviously suspicious prompt directly. Unsafe instructions can arrive through context that looks like ordinary project material, retrieved content, or routine tool output. That's why repository, network, and tool-provided context should all be treated as potentially hostile. Now, potentially hostile doesn't mean every input is malicious. It means familiarity isn't proof of trustworthiness. Just because a file is inside the project, that doesn't make every instruction inside it safe. Just because network content is relevant, that doesn't make it authoritative. And just because tool output is machine generated, that doesn't make it harmless. So the useful mental model isn't the agent knows my code base. It's the agent is processing inputs from several trust domains. Once we see context as a collection of inputs, the replacement for that false comfort becomes much clearer. Context needs an explicit boundary. Start with what should never enter that boundary: credentials and sensitive files. Exclude them deliberately from AI context instead of assuming version control exclusions will handle the job. Then look closely at what is allowed in. Repository content, network material, and tool-provided information should all be handled with a hostile input assumption, because any one of them can expose the agent to indirect prompt injection. Those two controls solve different problems. Explicit exclusion reduces unnecessary exposure of sensitive information. Distrust of admitted inputs addresses the possibility that allowed context contains manipulative instructions. Put simply, one governs what gets in, the other governs how whatever gets in is interpreted. Neither control guarantees security. Context controls reduce exposure and create clearer trust boundaries. But an agent can still produce a bad change. And that brings us to the midpoint of the policy. Protection can't end at the prompt. Suppose the context boundary works exactly as intended. Sensitive files are excluded, external inputs are treated cautiously. Is the generated code ready to accept now? No. Context, discipline, and output verification are separate layers. The next question isn't whether the agent sounded confident or produced a plausible-looking diff. It's whether the change survives checks that actually produce evidence. AI-generated code should be validated through compilation, automated tests, warnings, and static analysis before it's accepted. Compilation checks whether the code satisfies the language and build constraints. Automated tests exercise expected behavior. Warnings surface suspicious or fragile patterns that might not stop a build. Static analysis examines the change for detectable issues without relying only on runtime execution. These aren't decorative steps added after the real decision has already been made. They're part of the decision itself. The output remains a proposal until verification produces evidence that supports accepting it. This shifts the acceptance standard from authorship to evidence. A developer-written change and an AI-generated change both need verification, but an agent's polished explanation should never stand in for those checks. A practical gate can ask 4 direct questions. Does it compile? Do the automated tests pass? Are relevant warnings resolved or understood? Does static analysis pass? A failure in any lane is useful information. It isn't an inconvenience to wave away just because the generated code looks reasonable. Of course, passing these checks doesn't prove a change is secure or correct in every possible situation. Compilation can succeed while the behavior is still wrong. Tests cover only what they actually exercise. Warnings depend on the rules you've configured. Static analysis has boundaries too. The value comes from combining all of them into a repeatable acceptance process instead of trusting a single signal. The principle is straightforward. Confidence isn't evidence, and fluency isn't validation. Generated code earns acceptance by moving through the same visible gates every single time. Even a verified change can behave differently after deployment. That makes production the final feedback loop, not a victory screen. Production AI systems need logging, monitoring, and alerting to detect degradation and support root cause diagnosis. Logging preserves useful records of behavior and events. Monitoring turns ongoing behavior into signals a team can inspect. Alerting brings meaningful degradation to someone's attention, instead of requiring a person to notice it by chance. Together, these capabilities answer 2 different needs: detection and diagnosis. First, did the behavior degrade? Then, what evidence can help explain where it happened and why? Without both, teams may miss a problem entirely or struggle to reconstruct it after someone finally discovers it. Observability doesn't guarantee that every failure will be caught. What it does is create a feedback loop that makes production behavior more visible and makes investigations more grounded. So the policy extends across the whole workflow: inputs before generation, evidence before acceptance, and signals after deployment. At this point, we can replace the idea of a magic file with a 4-part AI development policy. First, explicitly exclude credentials and sensitive files from AI context. Don't assume ordinary version control exclusions are protecting them. Second, treat repository, network, and tool-provided context as potentially hostile. Coding agents can be exposed to indirect prompt injection, so admitted context shouldn't receive automatic trust. Third, verify every generated change before acceptance through compilation, automated tests, warnings, and static analysis. The output is still a proposal until those gates produce evidence. Fourth, monitor what happens after deployment. Production AI systems need logging, monitoring, and alerting so teams can detect degradation and support root cause diagnosis. These layers don't guarantee security. They create explicit boundaries and repeatable decisions where assumptions used to stand. Gitignore can keep doing its version control job. The security policy has to do the larger job: controlling context, distrusting inputs, validating output, and observing production. Here's the concrete next step: audit. One AI-assisted development workflow this week. List the credentials and sensitive files present in its environment. Then verify that they're explicitly excluded from AI context. Don't stop after confirming that they appear in gitignore. Inspect the actual context boundary the workflow uses. Next, trace the acceptance path for one generated change. Identify where compilation runs, where automated tests run, how warnings are handled, and where static analysis is enforced. If any check depends on somebody remembering to run it manually, record that gap. If a failure can be accepted without review, record that too. The goal isn't to claim perfect protection, it's to replace invisible assumptions with controls you can actually inspect. Start with one workflow. Document its context exclusions and verification gates. Then use what you learn to define a policy your team can repeat. If this framework helped you see AI-assisted development more clearly, subscribe to Neural Stack, like the video, and share in the comments which part of your agent workflow you plan to audit first.